In this video, I'm going to introduce you to polynomial functions. Polynomial functions, poly just means many, so anytime you have a function with multiple terms or many terms, it could be described as a polynomial function. And we have lots of different types of polynomial functions. You've already seen some. Linear functions and quadratic functions are all polynomial functions as long as they have many terms. So in this video, we're going to be focused on a couple vocab words here. This is called a leading term. Leading meaning being in the front, and term being this whole thing right here. So we got 1, 2, 3, 4, 5 terms in this polynomial function. The leading term would be the one in the front, or if it's out of order, which doesn't always happen, but sometimes, the term with the highest exponent or highest degree is going to be your leading term if you put it in order. So exponent, power, and degree are all talking about the same thing. We're all talking about this number right there. And degree or exponent all means the same thing. And I think that's good on the vocab. We can start to talk about end behavior, which is really what the focus of this video is. So what does our graph do at the farthest left side and the farthest right side? What's going on at the tips of our graphs? So all we're going to do is focus on this leading term and the degree or the exponent. It's going to give us a lot of information. We'll be able to sketch graphs of polynomial functions. And to be honest, sketching is probably the most important thing. You can learn how to graph this polynomial function by hand without a calculator. It takes a lot of steps and it takes a lot of time. And so nowadays, since we have graphing calculators, it's just a lot easier if we just use the technology and check our work using these skills I'm about to show you. Alright, let's get into a graph. So the first type of polynomial function would be a linear function. So if I have something like this, hopefully you're familiar with that type of graph. It would just start at 1 and have a slope of 1 over 1. So it would do something like that, and obviously keep going in this direction as well. And as it turns out, any polynomial function with a exponent or a degree higher than our 1 here, as long as it's odd, meaning 3, 5, 7, 9, and so on, our graph is going to look very similar to this. But all that's going to differ is that we get a little bump in the center. And that bump can vary in height and width depending on what our function is really doing, but so it's going to get that type of a bump there. And that's for anything with a degree higher than 1 that is still odd. So for example, this might be a graph that represents a cube function. But maybe it's not entirely accurate, but at least the end behavior is definitely accurate. So that's why we use our graphing calculator, just to be really accurate about what's going on in the middle here. But since in this video we're just talking about end behavior, I don't want to get into the specifics of what's in the middle there. So on the ends, that's what we're really focused on. So the left side, end behavior. So what's happening here, we're going to describe it in terms of inputs and outputs, or x values and y values. If I move left with my inputs or my x values, my outputs are going to go more and more down, right? They're going to go more and more negative. So we use that and describe it like this. Since we're talking about functions, our output is going to be described using function notation. This is just a fancy way of writing y, or output. So our outputs are approaching, that's what this arrow means, approaches, goes closer or moves towards, approaches negative infinity. If I were to continue to go down forever, I would approach infinity, but since I'm going down on my y values, that's negative, I'm going towards negative infinity. And that happens as my x values, or my inputs, are approaching negative infinity as well. So if I plug in more and more negative x values or inputs, I get more and more negative outputs. So that's all this. It's just a fancy way of saying that. Let's try it out by describing the right side. And we always describe it left to right, just like you would read a book. So on the right side over here, my inputs are going more and more positive, and as they do that, my outputs go up. So they go more and more towards positive infinity, or they go higher. So my outputs on the right side are approaching positive infinity, as my inputs are doing the same. They're also approaching positive infinity. So you can see that the outputs are opposites of each other here. And that's true of all odd degrees. So anytime we have a positive leading coefficient and an odd degree or an odd exponent, this will be the pattern of our end behavior every time, regardless of the polynomial function. We could have x to the 5th, we could have x to the 11th. It would all have a similar end behavior. And what would be different is what's going on in the middle there. Alright, so that's for all positive leading coefficients. Anytime this number in front is a positive number, and this degree right here is an odd number, this will be your end behavior description every time. Alright, let's change it up just slightly. This time I'm going to have a negative leading coefficient, but I'm going to keep my degree odd. Okay, so let's say our leading coefficient is now negative, and our degree is still odd. So the simplest one would be a linear function, and we'll just change it up. We'll say now we have negative 2x plus 1. So now our leading coefficient is now negative. Our degree is still odd. It's still a 1 there. So now I would start, I'd start at 1 at my y-intercept, and I'd go down 2 over 1. And we can draw a line there. That would be the most basic form right there. So because our leading coefficient is negative, we now have a negative slope, or our line is going down from left to right. And if I increase my degree now to any other odd number, I could make it to the 5th this time just to change it up. It could be the 11th, it could be the 23rd power, it doesn't matter as long as it's an odd number. All that's going to change is that in the middle here I'm going to get a little bump. So now it's doing something like this. And again, it's not completely accurate, I'm just sketching it. Use your calculator to make a really accurate graph if you want. But we know our end behavior is going to be the same. This will always be in this direction, this will always be in this direction, as long as this is true right here. So let's describe our end behavior. We'll describe the left side first, starting with our output. Our outputs are going more and more positive as we move left. So our output, or f of x, is approaching positive infinity, as our inputs, or our x values, are approaching negative infinity. We're moving left on the x-axis. If I plug in a negative 4, I get a positive output, and if I plug in a negative 9, I'm going to get an even more positive, a higher output. So that is our left side end behavior. Let's focus on the right side now. Our output is approaching negative now. If we move to the right, now we're going towards negative infinity, as our inputs approach positive infinity. So as I move to the right on the x-axis, my values are going more and more positive, but my outputs are becoming more and more negative there. So again, we got an odd degree. Our end behavior outputs are opposites of each other, and that's with a leading negative coefficient. We're going down from left to right. So the easiest thing to do is just to keep in mind about that linear function, sketch that, but if you have a higher degree other than 1, know that you're just going to put a little bump in it. Kind of makes it easy to memorize. All right, let's talk about even degrees this time. So now we can think about our quadratic functions. So similar to if I had a function like this. Hopefully you're familiar with a quadratic function. I know that it would be doing something like this. Because my leading coefficient is positive, I know that my parabola opens up. And if I have an even degree, I know that the shape of my graph is going to be a parabola if it's a quadratic function, but it's going to be similar to a parabola if I go any higher than that, but I keep my degree even. So this is if degrees are even and leading coefficients are positive. If the leading coefficient is positive, we open up, and if my degree is even, I either have a parabola or it's going to be similar to a parabola. If I make it higher than 2, if I make my degree any higher, let's say x to the 4th this time, the only thing that changes is that we get that little bump in it. And the way the bump looks for these is like this. So it's kind of like a W. And we can describe the end behavior because it will always be the same, whether or not I have a bump. The arms are always going to be pointed in the same direction if my degree is even. So different than our odd degree, which were opposite directions. So now my output on the left side is going positive. It's going towards positive infinity as my inputs are going to the left or negative. So if I plug in a -3, I get a positive something. If I plug in a -9, I get an even more positive value. On the right side, my outputs are still going positive. They're pointed in the same direction. But this time my inputs are approaching positive infinity because I'm moving to the right. So hopefully you're starting to get the little patterns. And once you catch on, it makes it really easy. So that would be even degrees, and if my leading coefficient was positive. Let's change it up one more time. We'll make the leading coefficient negative this time. So let's say I have negative 2x squared plus x plus 1. Well, I know that if I have a quadratic with a negative leading coefficient, I'm going to have that umbrella shape, or my parabola is going to open down. So that's a leading coefficient that is negative. And now if I change it up, if I just make that degree a higher even number, so if I have a degree that's even, it's not going to change my end behavior. The only thing that's going to be different about this graph, aside from its width or its length or how much it stretches or whatever, it's just going to be that little bump in the parabola. So now we have more of an M shape. That's going to be true of all even degrees with a leading coefficient that is negative. It's just the same thing but upside down now. So our left side end behavior, our output approaches negative infinity this time, as our x values or inputs are approaching negative infinity. And my right side is going to approach the same, negative infinity, as our x values this time are going towards the positives, towards the right side. Alright, so that's end behavior. You can always sketch a little graph of your polynomial, know at least what the end behavior will look like, know what your outputs are going towards as your inputs are either going left or right, negative or positive. And that's a lot of the information you'll need in order to answer questions about polynomials without even having to, accurately sketch everything about the graph. So be able to just sketch these graphs out, just simply knowing whether or not the leading coefficient is positive or negative, or whether or not this degree is even or odd. And you should be alright. Good luck describing end behaviors and sketching polynomial graphs.